So now let's try to draw a Lewis structure for sulfur trioxide. I would like to use this molecule to go a little bit deeper into the phenomenon of resonance structures and what that means. So for sulfur trioxide, what I'm going to do is use the handy hints for drawing Lewis dot structures. And I'm going to go through this quickly, but feel free to pause so that you make sure that you understand each step. So in sulfur trioxide, I have one sulfur atom and I have 3 oxygen atoms. And I am going to kind of make a tally of the available electrons that each atom brings to the table and the required electrons that each atom is going to need for its octet. So sulfur brings 6 valence electrons to the table, as does oxygen. Okay, they are right on top of each other in the same column of the periodic table, so they both have 6 valence electrons. Now with oxygen, I need to multiply this by 3 because it's trioxide. There are three oxygens in the molecule, so that's going to be 18 electrons that are available. So 18 plus 6 is 24 electrons that are available from the sulfur and the 3 oxygens. Now, sulfur is going to need 8 electrons for its octet, and the oxygens are each going to need 8, and there are 3 of them, so that's 24 electrons that are required by the oxygens. Okay, so I'm just kind of making this little table here. So 8 plus 24 is 32 electrons that are required. So I subtract the smaller number from the larger number, so 32 electrons that are required, minus the 24 electrons that are available. That tells me how many electrons need to be shared. And if I divide that number by 2, that tells me that I have to have 4 bonds. Furthermore, if I subtract the number of electrons shared from the number of electrons that are available, I will be able to tell how many electrons are in lone pairs. So 24 available minus 8 electrons shared leaves me 16 electrons that are non-bonding. And those electrons can be found in lone pairs in the molecule. So now let's start drawing the molecule. I know that I have 4 bonds that I need to include and 16 electrons in lone pairs. My unique atom is most likely going to be the central atom. So I'm just going to draw sulfur in the center. And I'm going to start by drawing the single bonding or the sigma bonding framework for the molecule with the oxygen atoms. Oops, that's not a very pretty oxygen. With the oxygen atoms singly bonded to the sulfur in the middle. However, I have one additional bond that I need to spend according to my calculations here. So I'm just going to arbitrarily put that bond here. I could have put it anywhere though, right? I could just as easily have put it up here and left these bonds single. Equivalently, I could have put it here. I just made an arbitrary choice to put it in one spot, but I could have put it in any of those 3 spots and it wouldn't make a difference. Now, I also want to put in the lone pairs. I know that in each molecular structure, I have to have 16 electrons in lone pairs. So what I'm going to do is fill up everybody's octet. Sulfur already has 4 bonds, so it has 8 electrons associated with it. But the oxygens are going to need to have their octets filled up. So I'm going to put 6 electrons around that oxygen because 6 plus the 2 from the bond is 8. 6 here. And then this oxygen would only need 4 lone pair electrons for a complete octet. I am going to do a similar thing for this resonance structure. And finally, I'm going to add 4 to the double bonded oxygen and then 6 to the singly bonded oxygens over here. So now I have 3 structures that all contribute to a picture of the SO3 molecule. And what I'm going to do is draw double-headed arrows kind of connecting them. These double-headed arrows are resonance arrows, and they are meant to emphasize the idea that these are 3 resonance structures. So resonance structures are different structures that contribute to the truth of a molecule. Now, the truth is that none of these structures by itself is the real structure of SO3. The real structure of SO3 lies somewhere in between. I could draw it maybe as kind of a hybrid structure where that double bond is actually equally distributed among all of the sulfur-oxygen bonds. Okay, so the true structure lies intermediate. The truth is really some kind of hybrid between all 3 of these structures. And the SO bond length in SO3 falls somewhere in between a SO single bond length and an SO double bond length. So none of these structures is actually the totally true structure. One thing I did not do here was calculate formal charge. And there would be formal charge on these. Let's see. I think that we would have, you can verify this by calculating the formal charge using the handy hints. But each of these singly bonded oxygens is going to have a negative formal charge on it. And the sulfur is going to be 6 minus 4, looks like. So the sulfur is going to have a 2 plus charge on it. So in all of these, I have formal charges on the atoms as well. So these are 3 equivalent resonance structures, and all of them contribute to the truth of the SO3 molecule. This makes them different from the resonance structures that we drew for carbon disulfide. One of those was better than the other, but here they're all the same, just rotated 120 degrees.